Hello everyone. In this video, we will be studying spanning tree algorithms. A spanning tree is a subgraph T of the connected graph G, and it is a tree, that is, it is a cyclic digraph which includes every node of G. In a graph G, there are n nodes and m edges. Then a tree must contain n minus 1 edges, and hence we remove m minus, that is the number of edges in graph G, minus n minus 1 edges from the graph, such that we get a resultant spanning tree. Consider the example where the graph G contains 4 nodes and 1, 2, 3, 4, 5 edges. According to the definition of tree, for 4 nodes, there must be 3 edges to obtain a tree. So we need to remove 5 minus 3, that is 2 edges from this graph to obtain a spanning tree. And this is obtained by removing any 2 edges. We get this 8 different spanning trees. Let us understand a weighted graph is a graph having weights assigned to every edge of that graph. For example, if we consider the electric lines supplying electricity at our homes, then every edge has some amount of electricity flowing through it, and it is the weight of that particular edge. So this is what is the concept of weighted graph. Let us understand what is a minimal spanning tree. We have seen a spanning tree is a tree which is the subgraph of the given graph having number of nodes minus 1 number of edges. So n minus 1 number of edges. So a minimal spanning tree contains n minus 1 number of edges, and that too the edges with the minimum weight. So a spanning tree of a weighted graph having minimum weight is called minimal spanning tree. Here further we are going to study algorithms to obtain minimal spanning tree using Prim's and Kruskal. In Prim's algorithm, we can obtain a minimal spanning tree where input is the undirected connected weighted graph and output is the minimal spanning tree. The algorithm starts with any vertex and selecting an edge with minimum weight and considering the edge and the associated vertex as the part of the desired tree. At each step, we go on selecting a node which is connected with the smallest weight, joining the node already present in the spanning tree. Again, we need to take care that this does not form a circuit. We repeat this step until all the vertices of graph G are included in the tree, and we stop the algorithm at this particular point. Let us obtain the minimal spanning tree for this given graph using Prim's algorithm. For this, to start with Prim's algorithm, first of all, the given graph contains 6 nodes, so the resultant spanning tree should contain 5 edges. According to Prim's algorithm, we can start with any node. So let us consider node F. From node F, node C and node E are adjacent, out of which the node C is the nearest neighbor with edge CF having minimum weight as 1. So let us include that edge CF in the spanning tree. Next, from nodes C and F, let us find a node having edge with minimum weight. So from C and F, we can find node A, which is having minimum weight 4 from C. So HCA is now part of the minimal spanning tree. Now we consider the nodes A, C and F and try to find the nearest node from any of the three nodes. We can find node B, which is nearest to node A, with the edge AB having minimum weight as 2. Now from nodes A, B, C and F, we need to include node either D or E, which are not already present in the spanning tree, and the connection of these E and D with any of the nodes A, B, C and F, such that the edge will be of minimum weight. So we can find from B, D is 11, from C it is 8, from F, D is not exactly adjacent. So we can go with edge CD with minimum weight 8. And lastly, we are left with node E having minimum weight of the edge ED as 6, and D is already present in the graph in the spanning tree, and therefore we can include edge ED in the minimal spanning tree. So now here we have all the nodes of the given graph included in the minimal spanning tree, and hence we can stop the algorithm. Also, we can observe that for the 6 vertices, we have CF, CA, AB, CD and DE as the 5 edges in the minimal spanning tree. The minimal weight of this spanning tree can be calculated by adding the weights at the edges included in the spanning tree. So 1 plus 4 plus 2 plus 8 plus 6, we get minimal weight of the spanning tree as 21. Let us now understand Kruskal's algorithm. Again, the Kruskal algorithm helps us to get minimal spanning tree, that is the acyclic subgraph of the given graph G. Kruskal's algorithm is also applicable for the connected undirected weighted graph, and hence we start Kruskal's algorithm listing all the edges of the graph G in the increasing order of their weights. The algorithm starts with selecting edge with minimum weight, and if there are more than one edges with the same weight, we can arbitrarily select any one of them. At each step, we go on selecting edge of minimum weight from all the remaining edges. Again, the condition remains the same, that it should not form a circuit with the previously selected edges in the graph. This step we will continue until n-1 number of edges are selected in the minimal spanning tree, where n is the number of nodes in the graph G. Let us go with this example to understand Kruskal's algorithm. The very first step is we will list out the edges with their weights for Kruskal's algorithm. So this is the table that we form for the given graph with BC as 5. BD as 6, and you can easily understand that all the ages are listed with increasing order of their weights. In Kruskal's algorithm, we need to go on adding ages. So I have already placed all the vertices at their positions. We start Kruskal's algorithm with inclusion of the age of the minimum weight in the spanning tree, and hence first age to be included is BC with minimum weight 5. Next age is BD with the weight 6, and it does not form any cycle, and hence we can include BD in the spanning tree. Next age is CD with weight 10, but it forms a cycle here along with the ages BC and BD, and hence we will not include CD in the graph. Next age is BF with weight 11, and BF does not form cycle in the graph, and therefore we can include BF as the part of minimal spanning tree using Kruskal's algorithm. Next stage is DF with weight 14. This DF again forms the cycle with the already included ages BF and BD in the minimal spanning tree, and hence we discard this age DF. And we go to age AB with the weight 16, and as this age AB does not form any cycle, we include it in the minimal spanning tree. Next age is ED with the weight 18, and it does not form a cycle, so we include this ED. There are 6 nodes in this diagram A, B, C, D, E, F, and to get a minimal spanning tree, the number of ages required is 1 less than the number of nodes. So for 6 nodes we need 5 ages, and 5 ages are already included in the diagram. So we conclude Kruskal's algorithm when we are done with 1 age less than the number of nodes. So at this point we will conclude with Kruskal's algorithm, and again adding the weights on the ages of the obtained minimal spanning tree, we will get minimal weight as 56 for this particular graph. Let us sum up comparing Prim's and Kruskal's algorithms. In Prim's algorithm, we can start with any of the node and go on including the ages with minimum weight. In case of Kruskal's algorithm, we have to initialize with the age of the minimum weight in the graph and go on with the increasing order of the ages. The minimal spanning tree for Prim's algorithm grows with adding minimum weight nodes, that is nodes which are connected with each other with ages having minimum weights. Kruskal's algorithm, the minimal spanning tree grows by adding minimum weight ages. In case of Prim's algorithm, the selected node is adjacent to the set of nodes already included in the spanning tree, and thus the tree remains connected. In case of Kruskal's algorithm, we go on selecting ages, and hence it is not necessary that the nodes will be adjacent, and the tree may remain disconnected. Prim's algorithm is better for a dense graph, and Kruskal's algorithm is better for sparse graph. So this video will help you to understand the Prim's and Kruskal's algorithm thoroughly. Thank you.